Alright class, day 2 in this video lesson strategy that I'm going to give a shot. Today we are working on comparing linear functions. Now we've been working with linear functions already for a little under a week, about a week so far. So we know about linear functions. We know about rate of change. We know the rate of change is the same as the slope. We know the rate of change is our change in output divided by our change in input. Rate of change is the vertical change over the horizontal change. Rate of change is rise over run. There's so many things that it could be. And we also know that the initial value is our y-intercept. In our equation, it's b, the starting point on our graph. Today we're going to be comparing linear functions. Now you can do linear functions in a number of ways. One of the ways that you can see a linear function is one that most of y'all recognize. Something like y equals 2x plus 3. This is represented algebraically. Y equals 2 times x plus 3, where 2 is your rate of change and 3 is your initial value. Another way to represent this same information is in a table. Let's see if I can make a table for this. It won't be the prettiest table, but you'll get the idea. One, two, one, two. There we go. Here's a table of that same information. We know that the initial value is the y-intercept. We know we can look at a table, and whenever our x is 0, that's our y-intercept. Our initial value is 3, same as this problem. Then we look at our change in y, which is 1 to 3, it's positive 2. We look at our change in x, the change is negative 1 to 0, so our change is 1. Change in y 2, change in x 1, 2 over 1 is 2, which is our rate of change. And there's other ways you can look at it. There's word problems, there's mapping diagrams. But the ones we're going to work with right now are tables and equations. Now, if you were asked to compare something, let's say I asked you to compare... If I asked you to compare these two triangles, which one would you say was bigger? Or how would you go about comparing them? You could say this one's kind of sloppy, this one's not sloppy. Well, it's still kind of sloppy, but it's not as sloppy as that one. This one's bigger. I mean, there's lots of different ways you can compare them. But the point is, you can tell the difference between them. Comparing linear functions is the exact same thing. Except, it won't always be as obvious as comparing two triangles or two shapes or two people. It won't always be that obvious, but if you look at it, it'll make sense. So I'm going to do the equation y equals 3x plus 2. And then there's going to be a table next to it. I'm going to want you to compare the two based on information in it. Okay, so let's take a look at these. We have a linear function, and we have data from a linear function. But these are both linear functions. This is just expressed in a table. This is expressed algebraically. Now, if I asked you to compare the initial value, which one would you say was larger? This one. This one has a larger initial value. The initial value is the y-intercept. The y-intercept is where it crosses the y-axis. Now, where it crosses the y-axis on this one is 2. That's what b is in this equation. Y equals mx plus b. B is the y-intercept, b is the initial value. In the table, we know that our y-intercept is when x equals 0. Well, x equals 0 and y is 3. Okay. So we know that this one has a higher initial value. Okay. Now what about rate of change? How would you calculate rate of change? Well, we know what the rate of change is on this one because it's 3. Rate of change is the same as the slope. Rate of change. Now what is the rate of change on this one? Do you remember how to calculate it? Change in y divided by change in x. Well, our change in y, how do you get from -5 to -1? You add 4. -5 plus 4 is -1. So 4 is our change in y. How do you get from -2 to -1? Plus 1. So change in y over change in x, 4 over 1. Our rate of change is 4. So which one has the greater rate of change? This one. Because this rate of change is 4. This rate of change is 3. Now a lot of you are probably wondering, man, this is so boring. He's been talking to us for 6 minutes already. I'm never going to use this in my life. Alright, let me give you an example. And then we'll call it a day upon this lesson. Let's say you had 2 pizza places. One pizza place had large pizzas for $9. Okay, so your initial value is $9. The other place had a pizza starting at $10. So your initial value at the other pizza place is 10. Now, here's where the difference comes in. Pizza place number 1 charges $1 per topping. $1 per topping. Now remember I told you, if you hear the per, that means that that's where your variable is going to go. Per topping. So, $1 per topping, you could say is, well, $1, 1x. Let's take a look at this together. $1 per topping. Pizza 1, $1 per topping, plus the initial value, which is 9. And this is all going to equal the total cost at pizza place number 1. At pizza place number 2, their toppings are only 50 cents per topping. Now, I just did 0.5, but 0.5 you know is the same as 0.50, which is 50 cents. Now, their toppings are 50 cents per topping. The total price is 50 cents per topping plus the initial value of 10. Now, a lot of you are thinking, we're saying, well, Pizza 1 is obviously the better deal. Their pizza is only $9. Okay, that's very, very true. Their pizza is $9, which is cheaper than $10. And if you wanted one topping, well, this pizza will come out to $10. This pizza will come out to $10.50. But what if you wanted more than one topping? What if you had people who you had a lot of meat eaters? They wanted pepperoni and sausage and bacon, and let's say they wanted 4 toppings. Let's say they wanted 3 toppings. I'll even make it even closer. Let's say they only wanted 3 toppings. Which pizza place would be better? Okay. Well, let's make a table based on our equation. Let's say that 1, 2, 3. I'm going to show you the price differences at 1, 2, and 3 toppings. Okay. Pizza place number 1. With 1 topping, it'd be $1 for that 1 topping. So $1 plus the original price of the pizza, which is 9. 1 plus 9 is 10. But if you wanted 2 toppings at pizza place number 1, well, 2 toppings, $1 times 2 toppings is $2. $2 plus 9, 11. 3 toppings, $3, 9, 12. So your 3-topping pizza that you wanted, pepperoni, sausage, and bacon, or whatever you want. Maybe you don't like meat, so peppers and pineapple or whatever. It's kind of weird, but hey, you know, it's cool. Now, the other place, 1 topping, 50 cents. 50 cents for that 1 topping, $10 plus 50 cents, $10.50. So with 1 topping, pizza place number 2 is more expensive. Okay. 2 toppings. 2 toppings times 50 cents is $1. $1 plus 10 is 11. So with 2 toppings, now the pizzas are actually even. You're actually paying the same price at each place for pizza. And then we look at 3 toppings. 3 toppings times 50 cents is $1.50. $1.50 plus 10 is $11.50. So if you look at it, pizza place number 2, if you get 3 or more toppings, is actually going to be cheaper than pizza place number 1, despite pizza place number 1 having a cheaper initial value. This is why it's important to know. Now, am I saying that every time you go out to eat, to bust out your whiteboard and start making tables with T-charts and X's and no, I'm not saying that. But I'm saying it's important to be able to compare 2 different things. Linear functions are representations of actual data, actual things that people have. Just something to keep in mind. We'll be going over this in class tomorrow, so if you didn't quite understand every last bit of it, it's completely okay. Important thing is you to get a little intro into it so that whenever we do the work in class, you're not completely clueless. Well, this video was a little bit longer than 4 minutes, but had a lot of information to cover. Have a good rest of your day.